So this is part 2 of this video for example 6. I'm going to move on to part B here. So can every vector in R3 be expressed as a linear combination of the vectors in S? So again, like I did in that last video, I want to base this on an understanding of the concept of linear combination. So with part A, we were asked specifically, can we express this vector, 0, 5, 5, as a linear combination of the vectors in this set? And the answer was yes. Now what we want to know is, can I take a linear combination of the vectors in S? So let's say this is scalar number 1 times the first vector plus scalar number 2 times the second vector, scalar number 3 times the third vector. And this time I want to know, can I generate just any vector in R3? So maybe I'll put this as x1, x2, x3. And this is where x1, x2, and x3 can be any number. So let's see. This vector equation, like I said in the previous video, corresponds to this augmented matrix. So we would put these vectors as the columns, augmented with, so this is where we had 0, 5, 5 last time. Now it's going to be x1, x2, x3. Now the row operations are going to be the same. So I might focus on just echelon form and not so much reduced echelon form. So I might focus on getting a 0, say in this position here. So 3 row 1 plus row 2. I'm going to leave that -1 up in the top left corner. So I'm going to leave row 1 alone for now. And then do 3 times row 1 plus row 2. So that'll be -3 plus 3. 3 plus 2. This is the same computation from in the previous video, I know. -6 plus 11. Okay, but here's what's different. Now, this constant column, we have 3x1 plus x2. Now, I want to get a 0 in this bottom row on the left side as well. So we could do that with the operation 4 row 1 plus row 3. Make that the new row 3. So that'll be -4 plus 4, 4 plus 1, -8 plus 13, and then 4x1 plus x3. Now, to get a 0 in this position here, we could do negative row 2 plus row 3. So I'm copying the other rows first. So that'll be 0 plus 0, -5 plus 5, -5 plus 5 again. And then, well, here I might want to do a little scratch work. Let's see, so it's negative row 2, which has 3x1 plus x2 there, added to row 3, this, which is 4x1 plus x3. So let's see, that's -3x1. I know my 1 got a little sloppy here. That's a 1. Oops, I'm distributing the negative. So this should be minus x2 minus x2 plus 4x1 plus x3. So if we combine like terms, -3x1 plus 4x1 would give us positive 1x1 minus x2 plus x3. So that's what needs to go right here. x1 minus x2 plus x3. Now this system, remember that I said in that previous video that the answer to part A was yes, because when we row reduced the matrix, what we found was a consistent system. So the question with this one is, would this system always be consistent no matter what we choose for x1, x2, x3? And the answer here is no. This system is only consistent, let me write it down here, when x1 minus x2 plus x3 happens to be 0, which is definitely not the case for just every vector in R3. The answer there is no. Find a vector that cannot be expressed as a linear combination of the vectors in S. Well, okay, let's let this vector x be 15, 0, 0. x1 is 15, x2 is 0, x3 is 0. Well, then certainly this equation is going to say 15 equals 0. That's a false statement, so system would be inconsistent. Yeah, and I was going to expand on that, but really, I mean, I don't have anything else to say. What you would end up, for the vector 15, 0, 0, you would end up with a 15 right here, and then your last row, I might sneeze, your last row is going to be zeros across the board equals 15.